Hello everyone, our topic is sleep stage and REM1 detection using machine learning models. Our team member are myself, Yanting Wang, and my teammate, Roshan Yang. First of all, I will quickly go over the goal of our project and what we've achieved. Considering that current sleep staging doesn't perform as well on detecting N1 compared to other stages, our goal is to train a model that can predict N1 better. So we are interested in seeing how our dataset and model could influence the performance in predicting N1. We've tested both the sleep cycle model and the linear model. With the linear model, we try to cut sleep segment going from wake to N1 to any stages, to increasing the data ratio of N1. We also test data after bandpass filtering and ASR. At the same time, we adjust the model to only predict N1 and non-N1 stages. What we are going to demo here is the final model that predicts two classes. Next up is the demo time. Before we dive into the demo, let me quickly give you a preview of what we are going to show. First, we'll go over how we extract N1 segment from the sleep EDF database. Then we'll talk about what kind of processing we did on the data before training our models. Finally, we'll show you the result of our model training. First, let's talk about how we select the N1 segments. Since we need to determine when we are transitioning from being awake to N1, we first identify the continuous segment from wake to N1. Then we add the next segment after N1 ends. We also want to boost the amount of N1 in our data as much as we can. So if the segment before and after N1 are too long, we only take the bits that are within 5 minutes. And we can use MATLAB to view the segment we cut out. So this is the signal. And this is the annotations, and only 3 stages in each file. For artifact removal, we use a butter bandpass filter, and here's what we did. For EEG data, we only took signal from 0.3 to 40 Hz because the reference suggests that this frequency range is most helpful for sleep detection. And it is noticeable that the signal magnitude after 40 Hz is all 0. And we can also observe the difference before and after filtering. And this is the origin EEG data, and this is the data after filtering. For feature extraction, the features suggested in the paper do not sleep on traditional machine learning were used. This includes drawing 131 features from both the time domain and frequency domain. The feature of the 2 epochs before and after, as well as different time window features, are also considered. So in total, there are 1048 features. And because the whole extraction process takes around 1 minute, and it is a good idea to save the feature for later use, and we save the feature in the features folder. And finally, I will demo the model that we've trained. And this covers the feature extraction and the label changing part I mentioned earlier. And we use the SGD classifier as our linear model. And the training process itself takes about 15 minutes, so it's also a good idea to save the model as well. Therefore, we can import the model immediately and use different data for testing. And here are our findings. For the same dataset, compared to distinguish multiple sleep stages, when the test is only to identify whether it's N1 or not, the model's ability to recognize N1 has significantly improved. So in conclusion, we have trained a model that has the ability to classify the N1 sleep state in this project. We have learned that simplifying the test can effectively improve the accuracy of the classification. However, we still face the challenge of data imbalance. Therefore, in the future, we aim to further address the issue of data imbalance and find ways to mitigate its impact on our analysts. And that is our final project. Thanks for listening.